Hi, everybody. It's Professor Mitchell. Today, we're going to finish up chapter 5 or chapter 8, I'm sorry, by looking at determining the sample size. Increasing the sample size, holding all else constant, reduces the margin of error and produces a narrower confidence interval. The sample size needed to achieve a specific margin of error can be calculated given the following information: the confidence level and the population standard deviation. So the formula that we're going to use to determine the minimum sample size needed comes from the formula for the margin of error. So first we're going to look at the confidence interval for a population mean. Remember that the formula for the margin of error for a population mean is z sub alpha over 2 times the standard error of the mean. And then remember, the standard error of the mean is sigma divided by the square root of n. So we have that the margin of error is z sub alpha over 2 times sigma over the square root of n. So what we want to do now is solve this formula for n. So first we will multiply both sides by the square root of n, and then we'll divide both sides by the margin of error, which will give us this. And then finally, squaring both sides of this equation gives us the formula that we want. So the formula for the sample size needed to estimate a population mean is n equals z sub alpha over 2 squared times sigma squared divided by the margin of error squared. So I want to emphasize, in this kind of problem, the desired margin of error will be given. So for example, if sigma equals 45, what sample size is needed to be 90% confident of estimating the population mean with a margin of error of plus or minus 5? So first we'll find z sub alpha over 2 for a 90% confidence interval, and that's a value that we've worked with before, which is 1.645. Remember, that's the z-score that cuts off the top 5% of the standard normal distribution. And I believe you have a chart with the z sub alpha over 2 values that go with different confidence levels. All right, so now we have everything we need to calculate the required sample size. Remember, n equals z sub alpha over 2 squared times sigma squared divided by the margin of error squared. So that's going to give us 1.645 squared times 45 squared divided by 5 squared, which comes out to 219.19. So what this is saying so far is that the minimum sample size needed to be 90% confident of estimating the population mean with a margin of error plus or minus 5, that minimum sample size is at least 219.19. But remember, sample sizes are always in whole numbers. So in order for the sample size to be at least 219.19, you really need to make it at least 220. All right, so when you're finding minimum sample sizes, if n comes out to be a decimal, which it usually will, always round up. All right, I know you look at 219.19 and you're tempted to round it down because that's what you normally do. Always round these up. All right. The population standard deviation may not be known, and in that case, sigma can be estimated with the sample standard deviation S. And in order to do that, one way is to select a pilot sample, which is a small initial sample from the population, and then use the standard deviation S from the pilot sample as an estimate for sigma. All right, next we go to calculating the minimum sample size needed to estimate a population proportion. I'm sorry this box looks a little sloppy. I had to do some repairs on it because the formatting was all messed up. All right, so remember from the last section, 8.4, that the margin of error for a population proportion is Z sub alpha over 2 times sigma sub p hat. This is the estimated standard error of the proportion. And that estimated standard error of the proportion is given by the square root of p bar times 1 minus p bar all over n. And once again, we're going to solve this formula for n. So multiplying both sides by the square root of n and then dividing both sides by the margin of error gives you this expression, which if you square both sides, similar to the last formula, you get n equals Z sub alpha over 2 squared times p bar times 1 minus p bar divided by the margin of error squared. Now, in order to calculate the required sample size to estimate p, the population proportion, we need to know p bar, the sample proportion. So this is a little tricky because the question is to find the minimum sample size, which kind of suggests that we have not yet collected our sample. So how would we know p bar? Well, there are a couple of ways you can estimate it. First, you can select a pilot sample and use that pilot sample to get a value for p bar. If that's not possible, and this is kind of interesting that this works, you can just set p bar equal to 0.5. Setting p bar equal to 0.5 provides the most conservative estimate for a sample size, which is a sample size that is at least large enough to satisfy the margin of error requirement. All right, so for example, what sample size is needed to estimate with 95% confidence the population proportion of US citizens with blue eyes with a margin of error of plus or minus 5%. So assume that a pilot sample of 100 people found 22 with blue eyes. So first we'll find Z sub alpha over 2 for a 95% confidence interval. And again, that could come from your chart. We've used this value before, it's 1.96. And then calculate the required sample size using the formula that we just talked about, Z sub alpha over 2 squared times p bar times 1 minus p bar divided by the margin of error squared. That gives you 1.96 squared times 0.22 times 1 minus 0.22 divided by 0.05 squared. Notice that the margin of error for a proportion has to be written as a decimal. So you crunch those numbers and you get 263.69. That is the minimum sample size required. So again, if you need at least 263.69 people, then you really need at least 264 people. Always, always, always round those values up. And that's going to take care of section 8.5. We'll see you next time.